All right, so we're going to finish up one problem, or actually two little problems in chapter 9. They're not little, they're kind of big, but two problems in chapter 17, and then we're going to move forward to chapter 18. Okay? Now, I don't think they're going to give you anything this difficult. However, your degree of understanding to this problem will allow you to answer whatever the actual problem it is. Okay? So, the scenario that we want to be aware of is how to identify the pH throughout a titration. All right? So if we start, for an example, a titration of a strong acid with a strong base. Titration of a strong acid with a strong base, right? So we have HCl being titrated with sodium hydroxide. And we went over this one in class already, and it's an easy one because you just kind of think about the titration and, you know, strong acid, we're starting low here, going to a strong base. We're going to see something like this if we plot pH versus how much base we add, right? And as long as there's more strong acid, then that will govern the pH. As soon as you run out and you start adding excess base, then the concentration of base will govern the pH, right? So that's all we have to kind of know there, is we look between, in the titration, how much acid there is and how much base there is, and know which is going to govern the pH, and find out what the concentration of it is, and find out then the pH, okay? So, to start off, for example, if you have 2.5 molar HCl, that's going to govern the pH because there's nothing else, and it's a strong acid. That means 2.5 molar hydroxide ion. Negative log of that give you the pH, right? So that would be that. Now, if I had added some base, right, 15 milliliters of base, I can find out, do the calculations, find out the amount of acid that I have here. That'd be 2.5 times 0.025, right? And then find out how much base I add. 2.2 times 0.015 are 15 milliliters, right? And then subtract the amount of base from the acid and find out how much acid I have left over. And again, because it's a strong acid, that concentration there is going to be equal to the concentration of hydrogen ion. The negative log of that will give me the pH. Okay? In a scenario where we have a strong acid, strong base, and we've added extra base, we've titrated the reaction, we've gotten to this point over here in this reaction, then we can just identify how much excess base we have, identify the concentration of hydroxide ion, and then take the negative log of the hydroxide ion. Now let's do this one because there's one little thing, well, in all of these there's one little thing that you have to remember. So this is a review, we already did this one, but we'll just look at it again. A reminder, we wanted to know the moles of HCl and the moles of the hydroxide ion that we added, right? To find the moles of the HCl, we had 2.5 mole per liter solution, right? And then we added 0.025 liters of that, right? To get the moles of hydroxide ion, we had 2.2 moles for every 1 liter, and we added 0.03 liters in this scenario, right? So then we can find out 2.5 times 0.025, 0.0625, 2.2 times 0.03 equals 0.066. So we can just take our 0.066 and subtract the 0.0625, and that tells us how much base we have left over. All right, so we have identified how many moles of hydroxide ion are left over. Now what we need to do is, and this is the tricky part, or not tricky, but just got to remember that that's moles and that's not molarity. So we have to find the molarity by taking the 0.035 and dividing by the total volume, which is a mix of this 25 and that 30, so it's 0.055. All right, so after we divide that by, 0.055, then that will be the molar concentration of the hydroxide ion. And then we can do what? Take the negative log of it, right? Negative log of that value, and then 14 minus that value, will give us our pH. Okay? So, again, we did this one already, but the tricky part is right at the end there, remembering that you might not be solving for moles of material, or molarity, you're going to be solving for moles of material. Now, this is the last problem here then, a scenario where instead of a strong acid, we're titrating a weak acid with a strong base. All right? Again, the titration curve is going to look very similar, starting at acidic, going to basic. Whoops. Start over. Right? pH versus how much hydroxide ion we add. This is a weak acid going to a strong base, right? You can't tell here unless you know what the equivalence point is here. So if I were to show you that the equivalence point here is, let's say, 8.5, then that means that, you know, if it's a strong acid, strong base, the equivalence point is always at 7. But weak acid, strong base, the equivalence point will always be a little basic. Okay, then now we want to go through these scenarios again before the titration, for example, in the middle of the titration, and after we reach the end point, what will the pHs be? Okay, so here we have a scenario: 25 milliliters of 2.5 molar weak acid. Right. Well, this is easy to identify the concentration or the pH of this solution. You just look at the weak acid, use the Ka. Now the Ka is not here on the slide, but the Ka is, again, 1.8 times 10 to the minus 5. This is acetic acid. We've used it in many scenarios. So a simple ice table here, identifying the concentrations, and then setting up our equation here, we can find the pH of the solution before the titration begins. All right? And so that would be the pH right there. All right? Hopefully there's no questions there. This is something we've done many a times. Now, in a scenario where they've added some base for us now. Okay? In the previous scenario where we had strong acid and we were adding base, all we had to do was subtract the amount of strong acid that was consumed, and whatever strong acid was left was going to govern the pH. Well, it's not that simple here in this weak acid scenario, because when you have a weak acid scenario, for all the base that you add, you're actually converting that weak acid to, here we have it right here, to its conjugate base. And that conversion then results in a scenario where you have weak acid and its conjugate base, and that is a buffer. That's a buffer. So we can't just identify how much acid is left over and do an ice table. We have to, if we do an ice table, it'll have to be an ice table that contains an initial concentration of this stuff and this stuff as well, and then we do an equilibrium to find out how much H3O plus ion is dissociating. But what's easier is to use the Henderson-Hasselbalch equation. In the Henderson-Hasselbalch equation, we can identify the pH of a buffer by using the pKa and adding the ratio of the log of the dissociated acid with the associated acid. Okay? So in this scenario here, we can use this same calculation as the previous problem because we know how much, they told us that we're using the same amount of, same concentration of acid and the same volume of acid, right? So we know that we're starting off with 0.0625 moles of the acid. All right, 0.0625 moles of the acid. So now that's not the value that can go here because that's just starting off. But I'll write that down here. How much acid do we start with? Moles of acid, 0.0625. Okay? And we can also identify the moles of base. Moles of base, it's going to be 15, or 3.2 molar times the 0.015, right? That's 0.048 moles of the base, 0.048. Now, this is going to be helpful for us because these are basically the values that can go in here once we've adjusted them appropriately, okay? We started off with 0.0625, but then when we added this much base, we consumed that, but this also ends up being how much of the conjugate acid we make, right? Because it's a 1-to-1 ratio over here, right? You can see that the amount of hydroxide ion you add, 1, will be the amount of the acetate ion that you get. So the amount of acetate ion that we're going to have, this little one right here, right, is going to be the 0.048. So I can write down 0.048 as my concentration of dissociated acid. All right. Again, pKa plus the log will equal our pH. Okay. Now, how much of the associated acid do we have? Is it that? No, it's this minus this, right? Because we added some base, so we lost some. So I'll put that in there, 0.0625 minus the 0.048, and we get 0.0145. All right, so then the 0.048 divided by the 0.0145, that's my ratio, the log of that ratio. That's my value that I'm going to add to the pKa. Now, what's the pKa for this acid? Well, this is the Ka. I don't know if you remember, but you can get the pKa by taking 10 to the minus Ka if you've forgotten, but I remember that it's 4.74 because we've done this one about 1,000 times. Holy cow. All right, so 4.74 is my pKa. I'm going to sneak this value in here, 4.74. So I got the log of my ratio. I'm going to add it to 4.74, and that should be my pH, 5.259, 5.26. That should be my pH, okay? So instead of just looking at excess acid, you have to recognize that it's a weak acid. You're making a buffer by adding base, all right? You have to use the Henderson-Hasselbalch equation, all right? So we got 5.27 as a pH. Okay, now the last scenario that we have to well, there's actually two more scenarios that we want to be aware of. This is, the one scenario we want to be aware of is when you've reached the equivalence point of a weak acid. Okay, so when you've reached the equivalence point of a weak acid, the thing that governs the pH is the concentration of that conjugate base that you have. All right, so remember that when you've reached this point here, there's no excess hydroxide ion. There's no more acid. All you have is, so if this was an acid dissociating, all you have is this acid right here, right? That's all you have. And so that acid, or sorry, not acid, but this conjugate base, all you have is this conjugate base. And whatever the concentration of that conjugate base is, its interaction with water and that equilibrium to form the weak acid and some resulting hydroxide ions, the ice table for that, again, this is the Kb, right? Or, you can get that from the Ka. So this is something that we did before as well, so it's just a kind of a review. But the point is, at the equilibrium point, this is the equilibrium, or the factor that's going to govern the pH, the concentration of the conjugate base that you have. Afterwards, if you've added more base, then it's easy again. You don't have to use the Henderson-Hasselbalch equation because you've added, and here's a scenario provided for us, 30 milliliters of 3.2 molar sodium hydroxide. We consumed all the acids, and now we have excess sodium hydroxide. So if you have excess sodium hydroxide, just like the previous problem where we had a strong base and added excess sodium hydroxide, it'll be just the sodium hydroxide that will govern the concentration. And so you can take you can find the concentration of the excess sodium hydroxide, and then and that would be what? This was the moles of acid that we started with. This was the moles of base that we had in the previous problem. This scenario here, we're adding twice as much, so we're going to have twice as many moles of base. So 0.048 times 2. 0.096 now is the moles of acid or moles of base, sorry, that we're going to have total here. So 0.096, which is the moles of base. Subtract how many moles of acid there were, 0.0625, leaving us behind a 0.0335 moles of base, 0.0335 moles of base. And I'm tempted to take the negative log, but no, I have to divide by the liters to make sure I'm in moles per liters, so I know that I'm talking about the molar concentration of the hydroxide ion. So liters, how many liters? It's, again, our 0.055 or 55 milliliters. So I divide this by 0.055, and then that gives me 0.609, and then I just take the negative log of the 0.609, and that gives you the pOH, subtract, or use 14, subtract it from 14, and I'm left with the pH. All right, so, and that's the same as if you had done a strong acid and strong base. So that's it. That wraps up chapter, that gives us a good review and wraps up chapter 17. Chapter 18 is nothing terribly difficult, all right? It's not much new. I mean, there's a couple concepts, but it depends on the same understanding of equilibrium. We were talking about equilibrium reactions still, and we utilize Ks for those equilibrium reactions. But in this chapter, the types of equilibrium reactions that we're talking about is reactions where, as shown here, some solid is dissociating into its ions. And the amount of dissociation is very, very small. For example, the K for this solid dissolving into its ions is 1.8 times 10 to the minus 10. All right, so it's a small value. The suffix, or not the suffix, but the subscript for the K is called SP, which stands for solubility product, right? Because we're taking the product of the soluble components. All right, so they call it the KSP. It's how much ions is actually ionizable, how much molarity, what's the molar concentration of the silver ion and the chloride ion in their product. Okay? And if you think about it, if I were to have told you, here's X and Y, and it's solid, and it's ionizing into X plus aqueous and Y minus aqueous. If I asked you to write the equilibrium constant for this reaction, if I told you it was an equilibrium and I asked you to write the equilibrium expression or the mass action expression, you would write concentration of X plus, concentration of Y minus, over nothing because it's solid, right? So that's it. That would be the K for that reaction. Okay? So again, it's a reminder that we leave out the solids, and the questions that they ask are very similar to the questions we've already been asked here before. It's just having a little familiarity with what KSP means, and also reminding ourselves that solids are not in equilibrium expressions. There's also a lesson to be learned in this chapter about the fact that if some compound is considered insoluble, like an ionic compound that's insoluble, there's always some degree to which it's soluble. 1.8 times 10 to the minus 10, a very low value, especially for the product of these two ion concentrations. However, there is always some degree to which insoluble material will be soluble, and we can calculate how much there will be using these equilibrium constants for this reaction. All right, so then, write the mass action expression or the equilibrium expression for the dissociation of this salt. Okay, so I'll give you 45 seconds. Go. Look at your neighbors if you don't know what's going on. We're writing the equilibrium expression, kind of like this. All right, I think we should have it by now. Okay, so we had Ag2 going to CO3. If that dissociates, it's going to be 2 silver ions and a CO3 2- ion. Okay, and if that is our dissociation, then the K for this reaction is going to be the concentration of silver ion squared. Now, hopefully you remember the squared because of the stoichiometry, times the concentration of the CO3 2- ion over nothing, because silver carbonate is not a soluble compound. Okay? Very good. So, let's do it the second time with this one. All right, there we go. So we have the ammonium sulfate. If its ammonium sulfate is solid, now ammonium sulfate is generally not solid, but if you had a scenario where it was based on the temperature, then you would get 2 ammonium ions. Ammonium ion squared would be in the mass action expression, 1 sulfate ion, so ammonium ion squared times the sulfate ion. All right, so that's a little reminder that you don't include solids. So that's all we have to kind of gather from that part. Now, if we want to express the solubility of a given salt, like we want to know how soluble is something that's insoluble, right? I mean, the solubility rules just say soluble, insoluble. Just like we used to say weak acid, strong acid. Now we know there's varying degrees of strong acids, and there's also varying degrees of solubility, okay? And those solubility are equilibrium expressions and can be described by an equilibrium value that tells us to what degree the material solubilizes. And it's also valuable to kind of describe these in terms of molar solubility. So here's an example. If I have this silver chloride and I know that its KSP is 1.8 times 10 to the minus 10, how many moles of silver ion, or how many moles of chloride ion, or better yet, how many moles of the silver chloride solid actually dissociate? How many moles of this dissociation actually occurs? Okay, so we can do this, right? We can say, well, the amount that's going to dissolve, let's see if they give us, right down here. We can describe the equilibrium concentrations here in an ice table, right? And what value should we put in here for the initial concentration of silver chloride? Well, because this is a solid, it really doesn't matter. It doesn't matter. If you put 10 molar, 5 molar, 3 molar, 2 molar, whatever, it doesn't matter. Because it's insoluble, and whatever value is there is not going to change the solubility. Because it's a solid, it's not going to change the solubility expression. The expression, again, is going to be whatever the silver ion concentration is times whatever the chloride ion concentration is. And if in the equilibrium statement we recognize that these are x's, we start off with 0 plus x, right? Then we can just say that the K for this reaction will equal x squared, right? So then 1.8 times 10 to the minus 10 will equal our x squared, and x will equal the square root of that. All right, so if I have 1.8 times 10 to the minus 10, 10 to the minus 10 like that, 1.8 times 10 to the minus 10, and then I take the square root of that value, 1.3 times 10 to the minus 5 ends up being our value for x, right? And that's the concentration. This is the silver ion concentration, molar concentration. It's also the chloride ion concentration, right? And therefore, it's also the molar solubility of this stuff. is how many moles of this, and because this is a 1 to 1 to 1 ratio, right? X equals this. X tells us what the molar solubility is of that compound. So the answer is 1.3 times 10 to the minus 5 is the molar solubility. Okay? So, kind of easy compared to what we did before. There's no denominator generally because, again, we're dealing with something solid, right? And it's often just the x squared. Sometimes it's a little bit different because of coefficients, and those are some scenarios that we'll explore. So here's an example. Let's see if you can get this one. Pay close attention to the coefficients. You have 90 seconds. Go. Set timer for 80 seconds. Help your neighbor if you got it. All right, so if you look at an ice table of this, right, the change is going to be a plus 3x and a plus 2x. Now, why wasn't it just x? Because the coefficients, or the coefficients, right? And then, once you put that into a equilibrium expression, it's 3x cubed, because there's a 3 there, and 2x squared, because there's a 2 there. Right? Therefore, this value, 2 times 10 to the minus 29, is going to equal 3x cubed times 2x squared. Now, this is one where 3 cubed, people always say is 9, right? Now, 3 cubed is 27. So we have 27x cubed here. 2x squared, that's 4x squared there. What's 27 times 4? 108. So this is 108x to the 5th. And that's going to be equal to 2.0 times 10 to the minus 29. All right, so solve for that, and it should be 7.1 times 10 to the minus 7 molar. Let's make sure we're there. So we got 2 times 10 to the minus 29 divided by 188. And then we have to take the 5th root of it. Now, how do we take the 5th root of a problem? How do we take the 5th root of a value? Well, you got to remember that x squared, the square root of x is equal to x to the 1/2 power, right? The square root of x is x to the 1/2 power. Or another thing to remind you is the cube root of x is equal to x to the 1/3 power. Okay, let's see, is that, yeah. So now we want to take the 5th root of this value because we have this value, 1.06 times 10 to the minus 31. That is equal to x to the 5th. So now we need to take the 5th root of both sides, right? So I'm going to take this answer and raise it to the 1/5 power. Okay? So then that gives me 6.3 times 10 to the minus 7, which is the value of X, and is not the right answer. What did I do wrong? 2.0 times 10 to the minus 29. I see what I did. I typed in 188 instead of 108. Why didn't you guys tell me? All right. So let's try that again. 2 times 10 to the minus 29 divided by 108. And then I take the cube root of that, raise it to the power of 1 over 5. 7.13 times 10 to the minus 7. Okay, so there's our answer. All right, so again, pretty much the same things we've been doing, but we have to pay closer attention to coefficients and exponents because of the stoichiometry that's here. All right, but the X value there is the molar solubility. Now, if they had said, what's the concentration of, for example, the calcium ion? Well, if I wanted to know the concentration of the calcium ion, this value right here, I'd have to multiply this by 3. Concentration of the phosphate ion multiplied by 2. So whatever the equilibrium value is in your ICE table, the equilibrium statement here, that X can help you find its concentration, if that's what was asked for in the problem. All right, so what's the molar solubility of barium phosphate? Woo! Go for it. Go for it. 60 seconds. 60 seconds. Help your neighbor. Help your neighbor. All right, so you'll see that there's a trend here where if I have another scenario where I have a 3 barium ions and 2 phosphate ions, then it ends up being, again, 108x to the 5th set equal to our KSP. All right, so let me see. Am I going to get the right answer here? 1.3 times 10 to the minus 29 divided by 108. Raise it to the 1/5 power, or in other words, take the 5th root, 6.5 times 10 to the minus 7. So it looks like the answer should be C. All right, good. Another scenario here where we're asked to find the KSP. Right now we have to find the KSP given the molar solubility of 3 times 10 to the minus 5. Now, remember, the molar solubility is the X. It's not the concentrations, but it's the X. So, let's see if you can do this one. This is an 80-second problem. 80 seconds. Go. All right, so you guys finished up yet? Let's go over it together. So we have a salt, it's going to dissociate like this. We had to recognize that that's the ratio of ions, again, because we were told that it was a salt, and we see two of them, three Bs, right? 2 As, 3 Bs. We had to recognize the change. The change was going to be plus 2x because there's a 2 here, and a plus 3x because there's a 3 there, right? We had to then recognize that the KSP for this, the expression is our concentration of A's squared and our concentration of B's cubed. And then we need to recognize that this is the equilibrium expression, equilibrium concentration for that A. So we put that 2x into there. And this is the equilibrium concentration here, so we put the 3x into there. I know what this value is. 108 x to the 5th. Right? Same as before. So, 108 x to the 5th will be set equal to KSP. But we know x here to be 3 times 10 to the minus 5. So 3 times 10 to the minus 5 to the 5th times 108 should be what our KSP is. All right? So, again, in this scenario, they gave us what the KSP was going to be. Or no, they gave us what the concentration, the molar solubility was, and so we're going to solve for the KSP. So we got 3 times 10 to the minus 5. Raise it to the 5th power times 108. 2.6 times 10 to the minus 21. All right. Very good. One more here. This is a 45-second problem. Go. All right, so then, again, we recognize that the KSP is A times B squared here, and these are the equilibrium concentrations of A and B, right? So KSP is going to be x times 2x squared. Now, 2x squared is 4x. 2x times 2x is 4x squared, times x is 4x cubed. Right? So that value has to be set equal to our KSP, and our x in this scenario is what they gave us, which is 2.5 times 10 to the minus 6. That value cubed times 4 should be our solubility equilibrium value for this compound. So, 2.5 times 10 to the minus 6, cube it, times 4, 6.25 times 10 to the minus 17. All right, very good. Now, there's something called the common ion effect. Common ion meaning like not common as in boring or something you see every day. Well, kind of. It's something that's going to be around. So common meaning the solution has this ion in common with some compound that's trying to solubilize it. So, for example, the molar solubility of calcium phosphate, right? We have the KSP here. We could identify the molar solubility of calcium phosphate. But it'll be different if there's already some sodium phosphate dissolved in solution. Okay? That's because if you think of sodium phosphate, strong electrolyte, ionizes at the start, therefore you're going to have a certain concentration, again, 0.1 molar of this. Sodium's not the ion to be concerned about here because it's not in the ice table of the dissolving or the dissociating of the calcium phosphate, but the phosphate ion is in the ice table. So the 0.1 molar solution of phosphate is going to be utilized in the calcium phosphate ice table as the initial concentration of the phosphate ion. All right, we get the same shifts, plus 2x, plus 3x. We can drop the 2x shift here. That becomes helpful in solving the problem. Again, we can drop the 2x because look how small that is, right? Look how small that is. So we're only going to get a very small shift, and that x represents that shift. So we can just set this to 0.1. Our KSP value then will be the concentration of the calcium ion cubed times the concentration of the phosphate ion squared. All right, so we set this up, set that equal to our KSP, 2.0 times 10 to the minus 29. Okay, so 3x cubed times 0.1 squared. Okay, there we go. 3x cubed, 0.1 squared. Set that equal to our 2.0 times 10 to the minus 29. All right, calculating time. I'm going to put 0.1 in there, and I'm going to square it. And I'm going to take our KSP, 2.0 times 10 to the minus 29, and divide it by that 0.1. Then I'm going to have 9x cubed on the left, right? If I simplify this, 3x times 3, no, sorry, 27x cubed, 27x cubed. 3x cubed is 27x cubed. And then now we have that set equal to 2 times 10 to the minus 27 after I divide it over the 0.01. All right, so this value equals 27x cubed. I'm going to divide both sides by 27. And then I'm going to raise this to the 1/3 power, which gives me 4.2 times 10 to the minus 10. And that is going to be the molar solubility of this salt. Okay? Not too bad. Nothing terribly crazy here. Because, well, there's nothing terribly new. It's just that the term common ion isn't something that we're familiar with, but if we think about what it's saying, what the term sounds like, we should be okay. All right. So, why don't you do this one? Calculate the molar solubility of barium sulfate in 0.1 molar barium chloride. Remember, well, there's the common ion effect, therefore something in the barium chloride will likely affect the solubility of barium sulfate. Barium chloride is a soluble compound. Barium sulfate is not a soluble compound. The KSP for barium sulfate is 1.1 times 10 to the minus 10. Okay? So, 60 seconds, go! All right, so then, what do we got here? Our ice table is going to contain the 0.1 molar of barium. That's going to ultimately be the equilibrium concentration. Sulfate is just a 1, or, it's just x. So therefore, x times 0.1 will equal the KSP, and then we can identify the molar solubility. All right, very good. So what happens to the solubility of barium phosphate if solid barium is added? Does it improve the solubility? Solid barium chloride, is added. Does it improve the solubility, or does it increase the solubility, or does it not change? And I'll give you a hint. The answer is not D. All right. Talk to your neighbor. 13 seconds. Okay, so when you add barium into this solution that's trying to ionize barium phosphate, the barium is part of the ice equation as a barium ion, right? And so it's going to have a concentration of barium already as a product. It's going to push it back towards the reactants then, and that's going to decrease the amount of soluble material. So it's going to decrease the solubility. All right. That's a good place to stop for today. So, hopefully you took the time to go through this video and answer all the problems, and we'll see you guys next class.